Hi, this video is going to explain linearity and compare it from something that you thought you understood completely, which was linear functions. Okay, so in section 2.4 here, you see that Garfinkel introduces these two properties, and he says that these two properties define a linear function. Now, in the context of differential equations, when we say linear function, we're more so talking about a function as the concept of a mapping, and specifically in terms of the differential operators that we're talking about when we define the state equations for x prime. In that context, it's really going to be important that what we call linear definitely obeys these two properties, even though, as you'll see, what I thought I was able to call a linear function from before does not necessarily satisfy these two properties. So there's a little bit of mismatch between what we're going to be calling a linear operator here, or a linear mapping, and what we were calling a linear function in terms of algebra and pre-calculus. Okay, so maybe going through this example and trying to confirm or deny whether it obeys these properties will help you see what I mean by that difference. So we're going to take this function, f of x is equal to x plus 2, and we're going to try to see if it obeys each of these properties. So for this first one, the property says that if I evaluate the function at the sum of two inputs, x1 plus x2, I should get the sum of evaluating them each of the points separately. So I'm just going to go through this in terms of plug and chug and see whether or not that holds true. Like if I was going to take this function f of x and evaluate f of x1 plus x2, what I would do is wherever I see the x here, I would replace it with whatever's inside these parentheses, x1 plus x2. So on the left-hand side here, evaluating f of the sum is equal to x1 plus x2 plus 2. You see, all I'm doing here is I'm just replacing the input here right where I see the placeholder for the input right there. So I have whatever's inside the input plus 2. Okay, now is that really equal to evaluating it for just x1 and then adding the evaluation for x2? Let's see what that would be if I just do the same plug and chug thing for the right-hand side of the statement. So f of x1 would be x1 plus 2. That's what that would be. And then f of x2 would be x2 plus 2. Okay, now I know that I can combine like terms here, so 2 plus 2 is 4. And so that's equal to x1 plus x2 plus 4. Okay, wait a minute. So on one side I got x1 plus x2 plus 2, and on the other side I got it plus 4. And so those are not going to be the same. And so you see a function that's even as simple as x plus 2 does not obey this first additive property. What about this property over here, which says that if I evaluate an input where I've multiplied x by some constant, some scalar a, that's going to be the same thing as multiplying the scalar a times f of just x itself. Again, let me just try out the plug and chug on both sides and see what happens. Just like before, if I'm doing f of ax, I'm just going to replace this placeholder for the input x with ax. So I'm going to get ax plus 2. Okay, that's what I get if I throw the ax into the x position there. Now, what if I do a times f of x? That would be a on the outside times the output where I'm just evaluating f at the input x. So that's x plus 2. And so if I just distribute the multiplier a here, I get ax plus 2a. So on one side I get ax plus 2, on the other side I get ax plus 2a, and those aren't necessarily going to be the same thing for all a. Those would only be true if maybe a is equal to 1, so that's not true either. Unfortunately, for the functional form of y equals mx plus b, which we thought was called a linear function before, that doesn't satisfy the two things, the two properties that define a linear operator. What we call linearity, or or combined together, what's also known as the principle of superposition. It's not satisfied when the plus b part on your linear function is a non-zero amount. Okay, and so in the context of differential equations, we're going to say that linear functions, linear in this context means mx, not mx plus b. If we use a b that's not equal to 0, as I just showed, it's not going to pan out with the linear properties. So in this case, we're only talking about linear functions being mx, okay? That's just going to be really important when we start to generalize linearity to the differential operators and the linear systems that we're going to see in the later parts of the book. All right, the other thing that's covered in this section is the concept of zooming in on a nonlinear function. And as you zoom in closer and closer onto one point of a function, if the function's a good function, it's gonna look like a line if you zoom in enough. Definitely crack open Desmos and plot any function you want, and then pick a single point and zoom in closer and closer and closer. Even if you thought that the function you chose was really curvy, if you pick a point and zoom in really, really, really close, you're going to end up seeing something that looks like a line, as long as it's well behaved. Okay, so zooming in, functions appear linear if they're well behaved. But what does it really mean mathematically to be well behaved? It means that you are a continuous function and you're also a differentiable function. So I'm going to show you examples of what it means to be continuous versus not continuous, and what it means to be differentiable versus not differentiable. All right, so the easiest way to explain the continuous property of a function is that you can draw your function without taking your pen off the page. So for example, if I draw a twisty, turny, windy polynomial, I can draw it with as many wiggles as I want, as long as I don't take my pen off the page when I'm drawing it and it's a nice continuous line. That's a continuous function. You'll understand what I mean more when I start to give you an example that's not continuous. Okay, so versus something that's not continuous, let's say that I have a line that's going like this, but then all of a sudden right here at this point, let's say maybe where x is equal to 3 or something, maybe the function outputs that value when it's equal to 3, but it makes a big jump. Like all of a sudden it goes up here and then it starts doing something else up there. If a function ever makes a jump, then I did have to take my pen off the page in order to illustrate that jump, and that function is no longer continuous. So that's one example of what we call a jump discontinuity, where I had to take my pen off the page and made this jump to another zone, and yeah, it made a little jump. It's not continuous. You may think that would never happen in real life, but it actually does happen sometimes. And the easiest example I can think of is like the way that rates are calculated when you try to mail something, right? Because it'll say like it's equal to, here, in order to do that, let me erase this. Let's say that we were trying to mail a package at the post office, right? And the x-axis is the weight of the package in pounds, and the y-axis is the cost of mailing that package. So as long as the package is, let's say, under half a pound, it's going to be a flat rate of like this much, right? But then if the package is between a half pound and a pound, all of a sudden the flat rate is that much. And so that, with little circles denoting the closed and open zone, is kind of a way, this kind of step function here is kind of a way that different rate amounts could be represented with a function that's not continuous. So it really does happen sometimes, and you can see that I did have to take my pen off the page. So far, those have all been examples of what are called jump discontinuities, but there's another type of discontinuity that you probably have encountered before. If you studied rational functions in depth in pre-calculus, then you saw examples of vertical asymptotes. A vertical asymptote is another example of something that's not continuous. For example, let's say f of x is equal to 1 over x squared. That function looks like this. On both sides of the y-axis there, as you approach the value for x is equal to 0, when x is equal to 0, you're talking about dividing by 0, and that is crazy. And if you try to divide 1 by 0, as you make the thing you're dividing by smaller and smaller and smaller, your output blows up to be bigger and bigger and bigger, and then you have a vertical asymptote right there. And that's what we would call an infinite discontinuity. And again, you see it coming down to the fact that in order to draw this function, I had to take my pen off the page and then put it back down on the page when I'm on the other side of the discontinuity. So, and if you wonder if your function's continuous or not, kind of a simple rule of thumb is, can you draw that function without having to take your pen off the page? Okay, so if your function is not continuous at a point, it will also not be differentiable at a point. But let me talk a little bit more about differentiability here, because that's the other property of a well-behaved function. Remember, well-behaved in this context means that when I zoom in on it closer and closer, it's always going to look like a line. The line that it always looks like as I zoom in closer and closer has a special name. Do you know what that name is? The tangent line. Right. The approximate, the tangent line that we're talking about is just the limiting concept of the secant line. That is the line that it starts to kind of look closer and closer to as you zoom in singularly on a single point. So if we're able to compute the tangent line at a point, since the slope of that line is the same thing as the derivative of that point, that's going to mean that it's differentiable because its derivative exists. So something that's differentiable, again, is just something that looks nice and smooth. And, there's so many different examples, but basically something that's nice and curvy and smooth, and it doesn't have too many crazy pointy spots. It's going to make more sense when I give you the counter example over here, right? So something, for example, that's not differentiable, actually in terms of a function that you're familiar with, is the function the absolute value of x. And so this is me illustrating the classic y is equal to absolute value of x. For positive x, that just looks like the line y equals x. For negative x, that actually looks like the line y equals minus x, because the minus gets canceled out for the negative x and then results in the absolute value. But what happens when x is equal to 0? That's when these two lines merge together at a really, really sharp, pointy spot. And so if you actually look at a graph of y is equal to absolute value of x, and you zoom in closer and closer and closer just onto the point x is equal to 0, that pointiness does not go away. That's the problem. If that sharp point is so sharp that when I zoom in, that sharpness doesn't go away, then I'm not going to be able to define a tangent line, and it's not going to be differentiable. So let me draw a similar example, which would kind of be an upside down absolute value function that I've translated upwards and over a little bit. Like if I had this kind of function, looks like a little tent or something, and it's basically a manipulation of the absolute value function, and there's that sharp point. What I want you to try to think about is how, if you thought you could define a tangent line, what would the tangent line look like? Because remember, the tangent line is always just brushing up against the function. Like over here, a tangent line at this point would look like that. A tangent line at this point would look like that. A tangent line at this top point would look like that. You see, no matter what point on the function I'm on, I'm able to define something that's just grazing the top of the function. And there's exactly one green tangent line that I can draw at each and every value of x here for this differentiable function. What I'm saying about this, calling it not differentiable, is that it's just not differentiable at this one point right here. So like maybe this is x is equal to 2. Now this function would be differentiable when x is less than 2. It would be differentiable for x greater than 2. But it's not differentiable at the point x equals 2 because I don't know how to draw my green line. Like, should I draw it like this? Or should I draw it like this? Or should I draw it like this? You see, there's not one unique tangent line with one unique slope that I can draw because it's so pointy there that there's all sorts of different green lines that I could draw that are seemingly just grazing that function right at the point x equals 2. Remember, the slope of the tangent line is the derivative. And so if there's one unique tangent line for every point, that means the derivative is uniquely existing there. That's why we call it differentiable. But if there's more than one green line that it appears that I can draw, it's not differentiable because the derivative is not uniquely defined when we have a sharp point. Sometimes it's also called a cusp. So that's one way that functions can be not differentiable, but then there's another way that they can be not differentiable that's even more sneaky than that. And that's when you have a function that looks kind of like this. Okay, so this might remind you of the sigmoids that I was talking about before because I'm kind of drawing this S-shaped curve. And before when I was talking about sigmoids, I was mentioning that when the power gets higher and higher and higher, it gets steeper and steeper and steeper. Well, I'm not going to write down the functional form right now, but consider that there is some function, or there's a bunch of functions out there that you can write down where the steepness is so steep at that point that the tangent line is literally vertical, okay? So there are certain functions out there where at a certain point things are happening with such a steep rate of change that if you tried to draw the tangent line, you would end up drawing a vertical line. Now, what's the slope on a vertical line? Infinity. Yeah, on a horizontal line, the slope is 0 on a horizontal line. But on a vertical line, the slope is infinity. And infinity is not a real number. It's kind of a conceptual limit to bigger than the biggest number that you could ever think of. And so if the slope's infinity, the slope is not a number. And if the slope of the tangent line is not a number, it means the derivative is not a number. So it means that there's no derivative at that point. And so that's another example of a way that a function can be not differentiable. Even though a tangent line exists, it's because the tangent line has an infinite slope. In that case, that we would call it a misbehaving function, and it's not differentiable at that point.